Thanks for the introduction. And let me begin actually by presenting a typical pipeline for when you will propose a new approach for malware detection based on machine learning. First of all, you will propose either a new feature engineering and or a new machine learning algorithm, and let's call that approach X. To evaluate your approach, you will need to collect some data. And there are a lot of publicly available malware dataset that researchers have put on over time. Let's say that we manage to get 50,000 malicious applications. And let's say that we then crawl some applications from a benign store, because we need also to represent goodware. And let's say that due to API limit, we manage only to get about 10,000. And eventually, you also need some state-of-the-art approaches to compare against. So you can either access the code or implement them. And then you would then apply an evaluation that follows best practices from the machine learning community. A very typical one is k-fold cross-validation, in which you split the dataset into k-folds. You train on k-1 and test on the other one, and then you repeat the process for all the different folds. And in this way, you avoid overfitting a particular configuration of the classifier. And then if you repeat that for your approach X and state-of-the-art approaches A and B, then you can compare the performance of the different solutions with a k-fold F1 score. And you may find out that actually X is the best one. Otherwise, you would have to reiterate this process. And recently, a lot of papers actually in the past 2-3 years achieved very high performance, even over 99% in terms of F1 score. So we started wondering whether actually machine learning actually solved malware detection. But what if I tell you that there are 3 major issues in this pipeline that prevent the validity, that compromise the validity of the results? The first one is associated with the use of k-fold in a security context. And another 2 issues are associated with the composition of the dataset during evaluation. I want to now discuss in detail about the sources of experimental bias, and I would like to start by talking to you about temporal inconsistency in train and test splits. Let's say that we have a timeline and some applications. Their position in the timeline represents the moment in which they were released. Above the line, we have red malware. Below the line, we have goodware represented as little angels. And what typically happens in security is that due to the arms race between attacker and defenders, malware constantly evolves over time. And sometimes an entirely new type of malware appears, which is very different from what has been seen before. In machine learning, this phenomenon is typically called non-stationarity, but also concept drift or dataset shift. And the main problem is that machine learning algorithms work well under the stationarity assumption when IID is preserved. So let's say that now we want to actually apply a k-fold cross-validation approach with k equal to 2 for simplicity. We split the dataset into 2 parts. We use one for training, the other for testing, and then we can revert it. And what happens here is that you can see that the pale red malware that was circled before is now present in both sets. And in this way, the classifier has at least one example of this entirely new category that was from an entirely different distribution. And this does not represent a realistic scenario, because if we were to deploy this machine learning classifier, this new type of malware would have appeared only after some time. So basically, what's happening is that we are including future knowledge into the training set, and this inflates the performance of the classifier. This is not a novel finding. Kevin Alex and Brad Miller independently found and published it in 2016. but unfortunately, not too much change in the community. The second source of experimental bias is related to the composition, like to the consistency over time of the goodware and malware in your data set. And let's say that we have like 3 goodwares on the left with fancy space hats because they are from 2019. And on the right, we have some pretty old-fashioned malware, which was maybe from some public available data sets. And let's say that like last week, a new API comes out called the new underscore method, and is like enforced on all the goodware apps. So if we crawled the app today, all the goodware will have this method, and all the malware will not have it. A machine learning classifier is not a magic black box, and we learn an artifact. It will learn the artifact that new method is super fundamental for distinguishing goodware and malware, but it's completely unrelated to the maliciousness. The third source of experimental bias that we identify is related to unrealistic class ratios in the testing set. There are more case studies in the paper, but I want to show you an intuitive example to give you the idea. And let's say that we keep the training set fixed, and we modify the testing set. In particular, we vary the percentage of malware by downsampling goodware. So let's say that on the x-axis, going to the right, we have a higher percentage of malware in the testing set. I recall that the training set is fixed. And on the y-axis, we have scores. If we start by plotting recall, and it remains pretty constant. And if we look at the formula, that's because we're keeping the same total number of malware in the testing set. And the true positive and false negatives then do not change. However, the more we remove goodware from the test set, the more the precision increases. And the reason is that we are removing goodware that was possibly incorrectly classified as malware. So we are removing false positive, and the precision increases. But this, of course, also affects the F1 score, because that is just the harmonic mean of the two of precision and recall. And it just produces unrealistic results. Here I am in the green rectangle, I am highlighting the realistic percentage of malware in the wild in the case of an Android domain. And you see that this is on the left part of the plot, where the performance are much worse. But just by changing the composition of the data set, performance can get much better. To address all these issues, we propose an evaluation framework that we call TESSERACT that enforces experimental constraints to remove these sources of bias. In particular, we have 3 constraints. The first one forces that objects in the training set are older than objects in the testing set. The second constraint enforces that goodware and malware are from the same time period at all time in the evaluations. And the last constraint enforces the realistic percentage of malware in the wild in a particular domain. And as I'm telling you this, you may tell me this sounds pretty reasonable. So we did also a literature surveys on papers from the last 10 years in security, even published in top conferences. And to read this plot, let me highlight the NDSS 14 paper. The logo represents the domain, Android, and the bullets are either green. For example, in this case, green represents that the constraint is satisfied, the third one. So it used the right percentage of malware in the wild, but the other 2 were violated. So the thing is that this problem is really endemic through the community. And the fact itself that they violate the constraints does not necessarily imply that the results are wrong. The problem is that it's unclear if the results are valid. So we need to evaluate for each domain whether there is actually concept drift, how fast it is, and how much each of these experimental bias can impact the results. And there are two required ingredients to do this. First, we need a large representative dataset with timestamps in that domain. And secondly, we need state-of-the-art algorithms to actually both to evaluate the impact of the problem in a certain domain and to evaluate properly new proposals. This is why we originally decided to consider Android as a case study to quantify the impact of the problem in that domain. So we recently, the guys from University of Luxembourg are maintaining, started maintaining the Android dataset, which is an awesome collection of applications crawled over time. And we got from like multiple stores, so you have both goodware and malware applications, and we got about 130,000 applications, and with about an average percentage of, with an average of 10% malware, which a number which was derived from technical reports, measurement studies, and some private talk with some industry partners. And the dataset we use covers 3 years, from 2014 to 2015. From 2014 to 16. And then we choose 3 benchmark algorithms. The first one is, they represent kind of the state of the art in malware detection, in Android malware detection. And the first one is Drebin, uses a lightweight static analysis that checks for presence or absence of strings and URLs and APIs and other static elements, and relies on a supervector machine. The second one is a more computationally demanding, uses a more computationally demanding static analysis based on function call graphs and Markov chains to extract features, and relies on a random forest classifier. The third algorithm is a variation of Drebin that uses deep learning because we wanted to see whether non-shallow learning algorithms were performing differently for some reason in presence of concept drift. The first important thing is that we're not pointing finger directly at these papers. We're just using them as representative of the category. And we also use these because we were able actually to reproduce the results by either getting access to the code or the paper containing enough details to reproduce them. So we actually managed to reproduce exactly also the results that were obtained in the paper. So it speaks very high of the scientific standards. And we could not have done this study without them. And TESSERACT, as I mentioned you earlier, enforces 3 experimental constraints to remove bias, but also does more. It supports time-aware evaluations. Let's first consider the NDSS 17 paper, where on the y-axis we have the F1 score. And let's first see the best tenfold F1 reported in the original paper, which was about 99%. If we enforce the spatial constraint, so we put the right percentage of malware in the testing set, there is already a drop in the tenfold performance. So the right tenfold is the one where SIT3 is enforced, and it estimates the performance of the classifier in absence of concept drift, so it's kind of an upper bound on the performance of the classifier. And TESSERACT plots allows you to evaluate the performance over time. In this case study, we considered a time window of 2 years and the performance for each month. So 2 things. You can see that at any point in time, the performance is worse than tenfold. And the second thing is that the performance tends to get even worse over time. To capture this, we proposed a new metric, AUT, which is the area under this temporal curve that is defined in terms of a specific performance metric and a certain period of time in terms of number and granularity. So for example, in this case, it was F1 for 24 months. And now we have all the ingredients to compare the 3 algorithms. What is surprising is that actually the USENIX 17 paper, which was the worst one on paper, turns out to be the most robust over time, over 2 years. But if you're interested in the first 3 months, then the NDSS 14 paper should be your choice. This is fully tunable. So TESSERACT allows to do realistic evaluations. Practitioners can use it to do to evaluate new practitioners can use it to choose among different options in a realistic setting, experimental setting. And researchers can use it to evaluate new solutions. And all parameters in terms of time, window, and granularity can be adjusted according to needs. But in addition to evaluating performance, it can also allow to evaluate retraining costs in terms of labeling or quarantine if I need to reject elements that then need to be labeled manually at some point. And there are more experiments in the paper, and I invite you to read that. In particular, there is one on rejection that is based on a work that we published a couple of years ago at USENIX. I want to show you now just what happens to this pipeline when TESSERACT is introduced. Well, first, now next to the k-fold, we also have TESSERACT that enforces constraint C3 even to the k-fold and enforces and does time-aware evaluations. Then you need to pay attention also to how to collect the dataset. And now Androzu enables it for Android, and recently Ember has been released for Windows and supports this kind of analysis. And now when you compare the performance, you can you also have AUT, labeling cost, quarantine cost, and maybe you find out that actually approach B is the best one in presence of concept drift. To conclude, we've shown that actually malware detection is still an open problem, and machine learning did not solve it. We proposed TESSERACT as a way to do sound evaluations that take into account concept drift, that quantify the impact and allows fair evaluations of the classifiers. And we are releasing code, dataset, and features. The code has been implemented at this link, which you can also find in this paper. You can just drop us a line to get access. And already a lot of organizations had access to it. And that's all. And I'll be happy to take any questions.
OK. Thank you, Fabio, for the beautifully done presentation. Put a lot of time into it. You're welcome to ask questions. Again, if you have questions, please state your name and affiliation first. I think I'll begin. Let's assume I'm not trying to write a new algorithm, but I'm trying to write an actual malware antivirus detector which will be installed on mobile phones. So what would be the best strategy for me as an antivirus writer based on the conclusions from your paper?
So I think that deploying the machine learning detection model on the device is a relative, I mean, you're talking about deploying it directly on the device or developing something that is directly on the device?
I want to write the best anti-malware software. What should I do?
So if you're doing the evaluation, so if you want to detect malicious applications in the device, you can use this kind of evaluation to see how fast malware authors are changing their techniques, so you can quantify how much frequently you need to also retrain the model. There are more experiments about this in the paper. And the idea is that this tool also allows you to find trade-offs between different approaches and different retraining costs. Because if you need to retrain, you may need manpower of people being able to manually label it. So this can support actually realistic evaluation that simulate how your detector will perform in the wild.
OK, thank you.
Tudor Dimitris, University of Maryland, great talk. I have a question about C2. So you said that because of this, you may have artifacts. You may learn this, this new method. It's a robust feature. But is this temporal inconsistency the only way that you can get these artifacts, or aren't there more insidious ways that would affect your biases?
I think that I think this work is a great advancement in understanding how to remove experimental bias, but I also believe this is not the end of it. But
I agree. So let me rephrase. Do you think that this is the most important source of artifacts compared to the other possible sources of artifacts?
I think that one is just a subtle one because we didn't have time to do it yet, but we were planning also to do a study on understanding when the classifier is actually learning artifacts, especially if you start messing up with this temporal composition of the data set. I think that one is probably just the most tricky one because I don't remember if we eventually put something in the paper, but we definitely did experiments in which we tried to enforce C1 and C3, but not C2, and tried to mess up a little bit with it, and performance were like kind of dropping, but we did not quantify the impact of the problem. So I definitely think it's maybe not I think the major one remains C1, and also C3 in terms of actual impact on performance, but C2 is the most subtle one, which can change in completely unexpected ways. Maybe the classifier will still learn something significant, but.
Very brief question.
Did you experiment with changing?
Can you speak?
Did you experiment with changing the training dataset, the percentages in the training dataset?
I'm sorry, can you speak louder?
Did you experiment with changing the percent of goodwill versus malware in your training dataset?
In your testing?
That's what you did, but did you try to see what happens?
Yes. So actually, it's a nice question, and
we are behind schedule.
Yeah, sorry, but I can talk to you. I mean, if you're interested, you can read more in the paper. But changing the percentage of the composition of the dataset in the training set is fair game. We also devised an algorithm. It changes the sensitivity of the classifier into detecting one class or the other. So yeah, that is fair game, and there is more in the paper.
OK. Let's thank Fabio again for his presentation.